In this video, we will discuss some quantitative aspects of strengths of acids and bases. So, in one of the previous videos, we understood about the ionization constant K, right? So, concentration of products divided by concentration of the reactants, right? We took a case where AB is an electrolyte, and when AB is dissolved in water, it is, and it's a weak electrolyte, so it is dissociating partly into A plus aqueous ions and B minus aqueous ions, right? So in this case, we discussed it as concentration of A plus, concentration of B minus, both are aqueous, upon concentration of AB aqueous, right? Because concentration of H2O being a liquid, its concentration is 1, right? So this was the discussion we had. Now we just extend the same concept to understand the words Ka and K. K is nothing but for acids, this dissociation constant we write. So it is acid dissociation constant. So in general, K is a dissociation constant or ionization constant. This is nothing but acid dissociation or acid ionization constant, correct? In the context of acids. And similarly, Kb is, we can call Kb as what? Basic or dissociation constant of the base, or base dissociation constant, or base ionization constant, right? Now, Ka and Kb, just like K, are dependent on temperature, correct? So let's take examples now. Let's understand this in terms of an example. Okay, we want to understand the expression for dissociation constant for, let us say, acetic acid. So this is one of the questions as an example in the textbook. So I'm just taking up the same. So we can write the expression for dissociation constant for acetic acid. It's a weak acid, right? So we will write the equation first: CH3COOH aqueous plus H2O liquid. It's a reversible reaction, so H3O plus hydronium ion plus CH3CO minus acetate ion, right? We already discussed this. Now, instead of writing K, we can directly write Ka, or if you want to arrive at the expression, let's start with K. K is considering CH3COOH as the electrolyte, in this case weak electrolyte. The ionization constant in general K is concentration of product, which is CH3CO minus aqueous, multiplied by H3O plus aqueous, divided by concentration of reactants, which is concentration of CH3COOH aqueous and H2O liquid. Now, as I mentioned, concentration of liquid is 1, so H2O is 1. So this becomes CH3COO minus aqueous, which is its concentration, multiplied by H3O plus aqueous concentration, divided by CH3COOH aqueous, because concentration of water being in liquid is 1. Now this we consider as Ka, because we are talking about the dissociation of the acid. Similarly, other acids, weak acids also, we can mention the dissociation constant in a similar way. And as I said, like the dissociation constant Ka, which we discussed for electrolyte, this dissociation constant Ka also depends on temperature, and it is a measure of relative strength of acids. Similarly, let's say for a base, ionization of a weak base, let's say we discuss some of these examples also before closing this concept. Okay. Now, let's say weak base in general is BOH. As per our Arrhenius concept, it will release hydroxyl ion, so BOH aqueous, and its reversible reaction B aqueous plus OH minus aqueous. Correct. Now, just like ionization constant for acid, it's a ionization constant for base, and it is nothing but concentration of the products B plus aqueous and OH minus aqueous, their multiplication, divided by concentration of BOH aqueous, which is the reactant. or the electrolyte or the weak base. Okay. Example, we can say NH4OH, ammonium hydroxide is a weak base, and it dissociates into ammonium ion OH minus H. So we can write dissociation constant of this base NH4OH as concentration of the products NH4OH aqueous, its concentration multiplied by concentration of OH minus, which is hydroxyl ion, divided by concentration of the reactant NH4OH. Okay, concentration we indicate in square brackets. Now we will also understand about polyprotic acids. So I brought this concept in one of the previous videos. I just mentioned it. So what is a polyprotic acid? So there are acids like, let us say, HCl. It can only donate one H plus, whereas there are acids H2SO4. It has two hydrogen ions, so it can donate one hydrogen ion or release one hydrogen ion in aqueous solution, or all both the hydrogen ions. So acids that have more than one ionizable proton, okay, they are called polyprotic acid. So I will not say proton here, more H plus ion, because we are talking about Arrhenius concept. Let's say in Bronsted-Lowry concept we talk about proton. Okay, both are same, right? So now let's say we talk about H2SO4, which is a diprotic acid, and when we are dissolving it in water, it will become, because let's say it's only releasing one H plus, so it will become HSO4 minus plus, this is H plus OH minus, plus from H2SO4 one H is also coming, correct? Okay, so what we can write this as is, I can write it as, I'll change the font, H3O plus. Okay, so H2SO4 is releasing only one H plus in this case, and then in the next step HSO4 minus, again reacting with water, will give us SO4 sulfate, SO4 2 minus, plus again H plus plus OH minus, this is water, and this H plus is released by HSO4 minus. So again this can be understood as H3O plus. Okay, so here we have two dissociation constants for the base. I will write it as K1 for the first reaction. It is equal to concentration of the products, which is nothing but HSO4 minus and multiplied by H3O plus, and divided by concentration of the reactants. In this case it is H2SO. Now what we will do here is right side aqueous, aqueous, this is also aqueous, maybe here aqueous, liquid, aqueous, and aqueous. So here we can write aqueous. Now this is first ionization constant of this base. Second ionization constant is K2, which is again concentration of the products. In this case it is SO4 2 minus sulfate ion, aqueous, multiplied by concentration of H3O plus aqueous, divided by reactant concentration. Now K1 and K2 have different values. Okay, and the one which has higher values indicates the tendency or increased tendency of ionization of that particular category. Okay, understood? So this is about the polyprotic acids, and we will also understand about the dissociation constant of an acid or a base using a numerical. Okay, so let's take one numerical. we will say compute the degree of dissociation and percentage dissociation of acetic acid in zero point 0.1 molar solution of the acid. Given Ka is equal to 1.8 into 10 raised to minus 5, dissociation constant of this acid. And remember, this dissociation constant doesn't have units because it is a ratio of concentrations. Okay. Now, before we go into the specific case, let's again understand in a generic case. Let us say Ha is an acid, weak acid, and we are dissolving it in water. So we understood this concept in terms of weak electrolyte. Now just extending the concept to a weak acid before we solve this. So this acid will form H3O plus aqueous plus A minus aqueous, right? Now initial concentration before the dissociation happened, let us say this concentration was 3 moles per liter of the acid Ha, okay? And let's say in the initial this is 0 and this is 0, and at equilibrium now sum of the, if alpha is the dissociation constant, here it is mentioned as Ka is the ionization constant, so alpha is the degree of dissociation, let's say. So alpha alpha is a fraction, right? So C alpha has dissociated. So originally it was C, so C minus C alpha will be present of the acid, and C alpha, and here also C alpha, concentration of both the ions will be present at equilibrium on the product side. Okay, so we understood that ionization constant Ka now is equal to product of concentration of the products C alpha multiplied by C alpha divided by concentration of the reactant C minus C. When we take C common in the denominator, it becomes, numerator becomes C square alpha square, this becomes C into 1 minus alpha, and the common factor C gets cancelled out, and we have C alpha square upon 1 minus alpha. We understood as an electrolyte, now we are understanding that as acid. That is the only difference. Okay, using this, we will, and also we said for weak electrolyte like that, similarly for weak acid, alpha is very less than, lots of approximation. Degree of dissociation is very less compared to 1. So 1 minus alpha can be approximately considered as 1. So Ka can be approximately said as C alpha square. I just write it properly, C alpha square. Okay, and therefore we can write alpha as approximately Ka and divided by C and square root of that. Using this concept, we will solve the numerical. Okay, so here Ha is nothing but CH3COH. So Ka for CH3COH in our case is given as 1.8 into 10 raised to minus 5. That is given in the question. See the question. Okay. Now alpha degree of dissociation is nothing but approximately Ka by C. And in the question we are given Ka value 1.8 into 10 raised to minus 5, and concentration. Concentration is also given as 0.1 molar solution of the acid, 0.1 molar or 0.1 moles per liter. So let's write 0.1. Very simple. So 0.1 is, we already discussed, it is 10 raised to minus 1. So I write it as 1.8 into 10 raised to minus 5 divided by 10 raised to minus 1. This 10 raised to minus 1 on the numerator side will become 10 raised to plus 1. So 1.8 into 10 raised to minus 5 into 10 raised to 1. So when the base is same 10, so and the numbers are multiplied, so the exponents get added up. So minus 5 plus 1 will be minus 4. So it is nothing but 1.8 into 10 raised to minus 4 under the square root. This comes out to be 10 raised to minus 4 square root is straight away 10 raised to minus 2, and we only need to calculate the square root of 1. This comes out to approximately 0.01. So you not even need to find this value, just can stop there also. Now the second part is percent dissociation. We got the degree of dissociation. Percentage dissociation is the second question. Second part of the question. See here, compute the degree of dissociation and percentage. Percent dissociation is but Formula is number of moles of acid in the dissociation and divided by total number of moles of the acid. Okay, but in simple terms we can write it as degree of dissociation, which is nothing but alpha, which is now calculated. This multiplied by 100, right? So it's basically how much? 0.0134 into 100, which is nothing but 1.34%. The dissociation. Okay, so acetic acid is dissociated to very less extent, 1.34% only, as we discussed earlier. Similarly, we can also obtain for a weak base the general alpha is equal to approximately Kb upon C under the root in case for a weak base. Okay, hope this concept is clear. And in the next concept, we will next video we will discuss the self ionization of water.